Transverse waves oscillate perpendicular to their direction of motion. The particle moving up and down pulls other adjacent particles up and down in sync with it. This, in turn, makes more adjacent particles move up and down with other particles, and a wave is formed. Transverse waves are the more interesting aspect of waves, as they contain a lot more physics to discuss. Where longitudinal waves are not affected by polarizing filters, transverse waves are. Think of a polarizing filter as a letterbox. In order to get a letter to get into your house, it must pass through the letterbox in the correct orientation. If your letterbox is horizontal, and you try to force the letter through the gap vertically, it will be mashed and not travel through. This is the same for transverse waves. Longitudinal waves are effectively one-dimensional. What matters to a longitudinal wave happens in one plane. If it doesn't happen in the plane where the particle is vibrating and the wave is moving, a longitudinal wave doesn't care. A transverse wave, on the other hand, has two dimensions to it. It moves in one dimension and oscillates in another. A longitudinal wave can be considered as a tube or a dowel. If the gap isn't big enough for the wave to fit through, it won't go through. It doesn't matter about the shape of the gap. A transverse wave can be thought of as two pieces of wood slotted together to make an X shape. One dimension of a gap may be big enough for the cross to move through, but the other isn't. No matter how you orient the two long pieces of wood stuck together, you cannot get them through the gap. This is how you tell the difference between transverse and longitudinal waves. A longitudinal wave is unaffected by a Polaroid, but a transverse wave is.